Hi Science Nerdies, Mr. Riley here. I'm just going to do a quick little video here on spectra and spectral analysis. Really we're just going to cover just the basics here. Looking at our three different spectra here that we can observe, we have three different ones. Okay? First one, the continuous spectrum. This one looks like a rainbow. This would be something we would get if we looked at the surface of a really high density hot matter, the surface of a star, for example. So basically we're getting all the visible wavelengths emitted or produced by that object, and we are seeing a rainbow. Okay, the continuous spectrum is not going to be that important for us. The emission spectra and the absorption spectra are a little bit more important for us. So an emission spectrum where we would have a dark background and some bright lines, this one right here. This would be if we were looking sort of close up at an excited gas of an element. And so what we would see is we would only see the wavelengths that are being emitted by that excited element. Okay. Now, the most common one that we tend to look at is the absorption spectrum. And so this is when, if we had a hot object producing all the wavelengths of EMR, of visible light, and it passes through a cooler substance. Now, this is the spectrum that we would get probably when we're looking to analyze stars. So we're looking at all of the visible wavelengths being emitted, and then in the atmosphere of the star, in the cooler area around the star, those cooler gases are going to absorb only specific wavelengths. And that signature can help us determine which elements are present in that star. So this is one of the things we can measure by looking at and measuring the EMR from stars. So for an example of this, okay, so we have we look in space, we gather light from a star, we pass it through a diffraction grating, which spreads out the light into the spectra, and some of the wavelengths are missing. Those are all the wavelengths that were absorbed by those cooler gases in the atmosphere of the star. And by looking at the pattern, the signature, the fingerprint, we can figure out which elements are in that atmosphere, and that can help us, figure out a lot of other things, like where the star is in its life cycle, for example. So when we're looking at this, what we're looking to do is we're looking to match up the different bars here. So I see this here, these two right here. So this is telling me that I probably have boron in here. I also have this thick line right here and here. So I probably have boron in my star. Okay. Now let's look at helium. Now helium has this vertical line right here. I'll just change my color here. It has this vertical line right here in the sort of the yellow range, and I don't see that here. So I'm thinking that in the atmosphere of this star we don't have helium. Okay, and then let's measure it against hydrogen. So if we look at hydrogen, we see these two bars right here, and then I see those two right there. I also have this one, which matches up here, and that matches up nicely with boron, and then I have one more over here, and that's that one there. So it looks like hydrogen's in there. So by doing that analysis, I can say that in the atmosphere of that star, there's boron and there's hydrogen, and that can give me some clues about, to learn some more things about that star. Now the last thing we're going to look at here is called the Doppler effect. So by looking at the spectra of stars, we can learn a few different things, right? One is the composition of the atmosphere of the star, and the other is actually the motion of the star relative to the observer. And the way the phenomena of this is something that's called the Doppler effect. Now, oftentimes we talk about the Doppler effect when we're talking about sound, right? If you're standing on the side of the road and a car drives by, you hear this meow. So as the car is driving towards you, you get a high pitch or high frequency sound. The cars, the motion of the car is basically compressing the sound wave, so you get a higher frequency, shorter wavelength. And when the car moves past you, you get a lower frequency sound, and that's because now the motion of the car is, I guess, one way we can say it is stretching out the sound wave as it moves away from you, and we get this sort of lower frequency sound, so longer wavelength. And so this can apply to light as well. And so when we look at objects in space, sometimes we see them as being shifted one way or the other. Okay, so let me just draw a quick little diagram here. So if I have, where's my pen here? So I have an observer. Okay, here's my eyeball. Okay, what's wrong with the pupil there? Okay, and I have an object. So this is a star in space, and this is a stationary object. Okay, the light is reaching the observer. This one relative to the observer is still. Okay. Now, when the object is moving towards the observer, so here's a star. Okay, it's moving in this direction. That wave starts to become a little more compressed. So what this is going to do is it's going to shift the spectrum of that object towards the blue, or the higher frequency, shorter wave side of the spectrum. Okay, and if we are, so this would be toward, okay, and this is blue shift. Oh man, that's messy. And then I'll just finish my diagram here. You guys are kind of getting the picture. So I have that object, and it's moving away. It's gonna sort of stretch that out, and so this is moving away. Now, longer wavelength, lower frequency, it's going to be shifting towards the red side of the spectrum. So this would be red shift. Now, if we look up the diagram here, we can see, right? If you look at this bar right here, these two bars, okay, this would be the expected spectrum that we would get when we're looking at an object. And when we, if the object is moving away from us, it's going to be shifted a little bit to the red side of the spectrum. If it's moving towards us, it's going to be shifted a little bit towards the blue side of the spectrum. Now, just a little note, most of the stuff that we observe in the universe relative to us is redshift. And that's a piece of evidence for the expanding universe. So thinking of things like the Big Bang Theory. But I'll leave you guys with that. Good luck, and I'll see you next time.